a lot of what I'm presenting here is actually currently being done in destination Earth, but given that storylines are also very important in EERIE, we thought that we take the opportunity to have this storylines slot here and show you what's done in Destiny, because in principle the data are freely available, and it's about kilometer scale eddy-rich models. So that this particular type of storylines actually are available and can be used in the context of EERIE and beyond. And just to sort of make this point a little bit more clear, I mean, clear is you see here one of the objectives of EERIE, which is about producing actionable climate information, and especially when it comes to this actionable information, storylines of regional climate change is absolutely critical. And sort of, I'm touching on one aspect of storylines here this afternoon. I mean, there's not just one approach. I mean, storylines has become, quite an interesting topic with different approaches actually around. And here's actually one of the first EERIE papers on storylines where they describe a little bit the landscape of what's going on. And if you're interested in the different flavors of storylines, then this publication here is highly recommended. I will be talking about something specific related to events, and that uses a sort of a specific kind of technique that has actually been used in slightly different flavors already by some people before, including KNMI, where they looked into tales of future weather. So what I'm going to present to you here is related to some of these efforts as well. Just a little bit of a background on all this. I mean, what you see here is global mean temperature. I mean, Ed Hawkins' famous warming stripes, and they clearly show to everyone, something is happening, something transformational, something fundamental in the climate system. And if you zoom in, for example, in a country like Germany, I mean, still it becomes a bit more noisy, but still fundamentally the story is very similar. And even if you go really to the local scale, like Bremen, I mean, you clearly see something is happening, okay? And that's, the power of these kind of warming stripes. But I think what is always very important, sort of very challenging when you communicate with a broader public, is to really translate this into what that means on the ground and what that means to people. And in particular, how this 1 degree or 1 point something degree global warming translates and impacts extreme events. And, I find personally these kind of kilometer scale storylines or storylines in general, event-based that I'm presenting here, very powerful in making people, making the impacts of climate change more tangible, also to non-experts. Now, let me give you a little bit of sort of some motivation and do this by means of an example. And this is a heat wave in Europe, more specifically in Germany, and one that occurred on the 25th of July 2019 in the west of Germany near Cologne. Okay, and still today, even though this is around 6 or so years old, it is still the record-breaking heat wave that we have experienced in Germany, with temperatures exceeding 40, going up to 42 degrees in parts around Cologne. Now, the interesting thing is I do have a personal connection with that heat wave, because on that day I tried to go back from Brussels to Bremen, and I got basically stuck in Cologne because nothing was going anymore with the trains. And the problem actually was that the air conditionings didn't work anymore, right? And sort of all the trains, and most of the trains, I mean, AC was just collapsing. And I will come back to this point before, a little bit later. But certainly, once temperatures went beyond 37, 38 on that day, the air conditioning was gone. Now, I started around that time, but also a little bit earlier already. Always when these events happened, I started to wonder and ask myself 2 questions. If you would have the same weather map, same type of weather situation, but in, say, pre-industrial times, so without additional CO2 in the atmosphere, and perhaps without the effect of drier soils and so forth, how would this day would have looked like? What would you have measured in Cologne? What would be that number there in that screenshot from the weather app on my iPhone? And then related to that's of course an attribution question. How much of that is due to climate change? But then, of course, the next question is, this kind of, what would be on that? What kind of number would be on my iPhone, in a 2, 3, and 4 degree warmer world? And always thought this is not necessarily straightforward to get that number. And sort of that's when I became interested in sort of ways of doing that. And given that I've worked a lot with nudging in my previous job at ECMWF, that was one of the obvious things to do. The idea and behind the method is actually the realization that certainly in the exotropics, every single extreme event that we experience, windstorms, heat waves, flooding events, they have to do with sort of funny excursions and particularities of the jet stream here. And that's an animation that was produced by Michael Böttinger, who is here today joining us. It's nice to see. And yeah, so that's a realization. So the jet stream is driving extreme events. And, when we look again at this 25th of July, 2019, that's exactly what happened as well. There you see sort of that streamlines in sort of 250 or 300 hectopascal, and you clearly see this omega type circulation of a very strong block sitting over Europe. So this driving of that extreme events by the jet stream is here also very clearly visible for that event. But as I said, in the exotropics, you can link every single one, and that's something that we actually exploit. Okay. And the approach is to basically keep the same observed large scale or prescribe the same observed large scale atmospheric circulation, have that, but only change the background climate. So make, the atmosphere warmer, if you will, the soils drier and the oceans warmer, but that only indirectly, but I'll explain this in a minute. And this will allow us to isolate the effect of warming for any given weather situation. So what we do is we take a climate model, such as the one that we used at RV to contribute to CMIP6, or IFS FESOM that we used to contribute to Destination Earth. Then we take the model, and then in order to impose the observed weather in this climate model, we sort of spectrally nudge the winds in the upper troposphere at each time step towards reanalysis data, letting everything else untouched, okay? Temperature is untouched, moisture is the ocean, the sea ice, the land is untouched. Only a prescription of the upper tropospheric wind, so the jet stream, if you will. And then do that actually with this coupled model repeat that for different climates. And this is sort of illustrated again here for sort of our first set of these kind of experiments with RBCM, so using our CMIP6 simulations as a baseline. And so what we did is basically we picked one of these projections, SSP37T, okay? And then we started to rerun the period 2017 to now by basically taking the restarts files from the 1st of January 2017 of the coupled system, and then switch on the nudging, and then sort of within 1 or 2 months, really the full coupled system started to sort of go onto the trajectory that we have seen in observations. Okay, and the scale of this I will be showing a little bit later in terms of recovering the weather of the day in that period. Then we did the same for pre-industrial times, okay, restart files, sometimes in the 19th century, and then rerun with the colder atmosphere, the colder ocean, and sort of moister land, and rerun this with the weather of today. Repeated this for a 2-degree warmer world and for a 4-degree warmer world as well. And then, we had the weather of today in 3 different worlds, and then, you could make this comparison. Now, how does it look like coming back to our example case of this heat wave in July, on the 25th of July, 2019 in Germany? Here you see basically the weather map produced from the coupled model with nudging. So a coupled model that has been sort of brought in the sort of vicinity of the observed system by spectrally nudging, and you clearly see that it's very realistic in terms of the temperature compared to what was observed, with around 40 degrees in western parts of Germany. Now, the same weather map for a pre-industrial times can be seen here. And what you see is basically that, the 1.2 degree of global warming that may have happened in the time in between translates into something like a 3-degree warmer warmer temperatures. Okay, so 1 degree translating into 3 for that heat wave over Germany, and that's actually quite interesting. I mean, so it would have been clearly an extreme heat wave even without climate change, but climate change brought it beyond the 37 degrees. Remember that I was talking about the air conditions in the train. We know that air conditions of those trains on the tracks at those times, they were designed with a maximum temperature of 37. So, the maximum they estimated in terms of natural variability, not accounting for climate change. And here it was really this additional 3 degree, this increment that that made that happen and brought the system, beyond the point where it functioned. And this then is here the same weather map, but same kind of weather situation, but in a 4 degree warmer world. And when you compare now 4 and pre-industrial, that you can see that 4 degree global warming translates into something like a 10 degree warmer heat wave. So there is this enormous, for certain events, there's this enormous amplification. Now, some of this is well understood. We know the land warms stronger than the ocean, for example. That explains already something of the more than 4 degree. But what we also found is clearly some evidence for additional event-specific amplification in that event. And something we also found, for example, in another paper on marine heat waves that I don't have the time to talk about here today. But 10 degree is a lot. I mean, these are the temperatures in summer you experience in in the Middle East. That's dramatic. So this is all in terms of our CMIP, I mean, course resolution storylines, and a lot of what we've gained and learned, was done with these kind of storylines. But what we did in Destination Earth, that we did the same exercise basically with kilometer scale models. So 9 kilometer in the atmosphere and eddy-rich oceans. Okay, just to get much more local details, so much more local granularity, sort of reflecting the case for local information for decision making. And this is the same heat wave, but now averaged over a longer period from the end of June to the end of July. So it's a month worth of data, and that shows a different part. So this heat wave affected larger parts of Europe. You see Paris here in particular. And you clearly see again how things are going up. This time, sorry, we don't have in this kilometer scale yet a 4 degree warmer world. So in the kilometer scale, what we can do currently is pre-industrial, which is 1950s. We can do present day, and we can do 2 degree warmer world. And I hope that in a few months, we actually also will be able to do 3 degree of warming. But you clearly see that consistent increase. And here you see more local structure as well. There are also, for these individual days below here, you find the temperatures as well for the 3 different climates. And something that you see when you look at a bit more detail is actually that on every single day, and this is actually based on using 5 ensemble members, and that you see really for each of the climates, each of the temperatures are very clearly separated for each of the days. So showing that on every single day we are experiencing, there is an increment on top of us that is always going in one direction. That is sometimes a bit larger, sometimes a bit smaller, but it's always going in one direction. That's that's impacting us, and that's impacting weather. And that's why I strongly believe in the fact that climate change is impacting weather. When these of course, I understand this, you can't really blame climate change for the development of that blocking system. But okay, even if you have a block, there's lots of weather associated with that, and that is clearly impacted by climate change, especially if you look at a parameter like 2 meter temperature. But I mean, the benefit of these kilometer scale systems becomes actually much more powerful when you look at a different set of extreme events, more specifically flooding and strong precipitation events. And I would like to give you a bit of a an idea of a flavor how that works, and more focusing now really on the kilometer scale as well. For Central European floods in September 2024, sometimes also called Storm Boris, that hit parts of Austria, but also other parts in Eastern Europe. And this shows here on the left-hand side the evolution of actually precipitation. That is this light blue that goes from blue to purple. And then you also have the wind indicated going from weak, which is blue, to red is very strong. And what you are seeing here is on the left ERA, in the little bit coarser resolution that it has. And on the right-hand side, you see sort of this rerun of that event with the kilometer scale system that we are also using, by the way, in EERIE. That's sort of the EERIE configuration that we are using in free runs in the EERIE project, but here in the nudged configuration. And you see that Storm Boris was basically a cyclone sitting, sort of moving into the Mediterranean and then picking up moisture and then generating sort of northeasterly winds that were sort of hitting the Alps here and other mountain ranges in eastern Germany, and then leading to lots of precipitation. And you see that this nudging, we didn't touch precipitation, cloud, wind, is really powerful in capturing the essence of the development of these weather systems. And on top of that, it generates features, like these, topographic jets there in the Mediterranean, lots of local features that is actually highly realistic. And that's not there in ERA due to the coarser resolution. So I think it's a very, very strong case for saying, under present day conditions, a coupled model at the kilometer scale is really capable of reproducing the essence of the evolution of that event. Now, if you verify this by looking into accumulated precipitation over the sort of heavy precipitation period from the 12th to the 16th of September. You see ERA in the left, you see one of the highest resolution precipitation products in the middle, and you see then IFS FESOM nudging with nudging from Destiny was with the EERIE configuration. You see that on the right-hand side, and you clearly see that in terms of peak magnitudes, but also sort of generally the patterns and the mountain ranges that are affected, you see actually that model performed actually quite nice and well. These are then the views of accumulated precipitation in these different worlds. On the left-hand, counterfactual means now 1950s climate, so our proxy for pre-industrial. In the middle is present day, and on the right-hand side you see 2-degree warming, and you see, especially when you go to a 2-degree warmer world, sort of how precipitation goes up. And this is also reflected here by the time series, where you also see now nicely the existence of the ensemble members, that sort of this range is always min max of the ensemble, and then the ensemble mean is here the solid curve. And then you see for most of the time, actually, outside of this extreme event, no discernible impact of climate change is found on precipitation. But once this sort of wind hits, sort of this extreme event comes, strong winds hitting the Alps, then you see this separation actually clearly occurring. And there's a very nice way that we've done, sort of put together by Jan Wehner, who works with us at RV, he's into visual storytelling. This is part of a sort of a longer story, but it's, I think, a very nice animation that also again showcases this. And at the same time sort of looks sort of how the differences are accumulated, how the accumulations that are for the different climates, how they start to differ as we go along as these extreme events here, extreme event actually unfolds. Now, you may wonder, how well actually sort of the weather in more generally is reproduced by that approach, by sort of taking a coupled model and spectrally nudging the longer waves in the upper troposphere. And what you see here is over a longer period of time, that's from Armald's paper, you see the correlation here in the upper left. We can start with that for 2-meter temperature between these nudged runs and between ERA. And so if the nudging would be perfect in a sense in describing this, you would expect a correlation of 1, which is blue. And if there's no correlation or very little, then you would expect something like green, and like brown, and sort of green, yellow is sort of in the middle. And what you see here for 2-meter temperature is that in the exotropics, I mean, this nudging is doing a tremendous job, indirectly constraining 2-meter temperature by constraining the winds, the circulation, okay? You see also a sort of a difference. I mean, this works much better in the exotropics than it works in the tropics. But this idea of upper level winds and potential vorticity impacting weather is something that is much more powerful in the exotropics than it is in the tropics. Nevertheless, even there is certainly some skill we can see. But there are also sort of regions showing up in the exotropics where actually the correlation is not that large, and that turn out to be eddy ridge regions, for example, like the Gulf Stream. And that can be explained by the fact that, by nudging the upper tropospheric winds and jet stream, we certainly don't constrain the eddies in the ocean. I mean, they have their own instability and they are not constrained at all. So, some of this sort of reduction of correlation has to do there with the fact that eddies are present. In other regions like the Southern Ocean here, in the Weddell Sea, it has to do to the fact that there's a big bias. So if the same weather hits a region with or without ice, then that has a big difference in temperature, and therefore correlations drop there as well. So it's a combination of those. But in general, you see 2-meter temperature is very nicely represented. And you can look at other parameters as well. On the lower left, you see total precipitation, and there you see that sort of probably you have something like 0.7, 0.8, 0.9, so 60 or so % of the explained variance, which is quite sizable. But what you also see is associated with mountain ranges like the Rockies here, the Alps, or in Norway, the western side, that you see that correlations in precip go also up well beyond that. So I think in general, one can say that we can have quite a bit of confidence that this approach is very powerful in recovering the essence of the weather and the events that we are interested in. And it even sort of goes into parameters we do not actually touch in the model, but that sort of follow as a part of the coupled system. So I think you have seen that things, that this is probably a very powerful tool to sort of, give people information how climate change is impacting certain extreme events. Now, the question that I quite often received, especially in the first few years when we presented this, was always, yeah, but that's very nice, but you are prescribing the jet stream, and isn't the jet stream changing, and isn't that what is making temperatures warmer in Europe and more precipitation? So sort of assuming basically or saying, perhaps this warming and more extreme heat waves in Europe, not necessarily being so much a thermodynamic part, but being just the more frequent occurrence of high pressure systems that come with heat waves. Okay, and it sounds very reasonable, and I think we see very strong trends in Europe. The only thing is we don't really know. We can't really sort of establish causality there and say, is that natural variability or is this anthropogenic? But because I always was saying sort of from me looking into CMAP runs, and I didn't really see strong signals, perhaps a little bit of an extension and strengthening of the jet stream in sort of in winter, but certainly no clear evidence from CMAP in terms of more meandering and stuff, but it was sort of more hand waving. But then to put a little bit more substance to and sort of try to more thoroughly answer that question, I mean, Eva here and Helge, they sort of carried out some interesting experiments to address that point. And what you see here is the total change, the temperature change, the total with our coupled model, with our RVCM CMAP6 coupled simulations. Okay, no nudging at all. That's the climate change signal we are seeing here in winter. Then below you see the CMAP6 multi-model mean, and you see that they are very similar. Okay, Arctic amplification, a bit more warming over the land than over the ocean, and so forth. But the RVCM seems to be very comparable to the full CMAP6 richness and ensemble. This upper right one is basically, if we look at the climate change signal for the period 2017 to today, when we nudge the winds, okay? And that is, if you will, the thermodynamic part of the change. Prescribing the winds, having them unchanged, but only having more CO2 in the model that then leads to warming or the knock-on effect. So basically, we're just increasing or changing CO2 and changing aerosols, but otherwise the coupled system is responding. And what you see is that basically in terms of temperature change, these sort of thermodynamics only, the climate change signal reveal by prescribing the jet stream and not changing it, but only CO2 and aerosols, the external forcing, we get basically the full signal, most of it. And the lower right part is what is left. That's from experiments, very interesting experiments as well. There we took the same climate, the same CO2 and aerosols, but then we nudged this model for these sort of present day climate, for example, but we nudged it once against the winds of the future, once against the winds of the past, and then looked at the difference. So same atmospheric composition, same external forcing, but the winds of the future compared to the winds of the past. And what you see is there are some changes, but they are an order of magnitude smaller. Now, this is valid only for temperature. If you look at precipitation, the dynamic component becomes a little bit more sort of more important, and in some part more than another. But fundamentally, the story that these, by nudging and prescribing the jet stream, that we get the essence of some of the mean climate change patterns. That is something that holds. Okay. Perhaps very briefly in this discussion, what is actually constrained in these kilometer runs with nudging? It's not as simple as dynamic and thermodynamics. I mean, what we are nudging and prescribing is the large-scale flow, so all total wave numbers smaller than 60. Basically, that means we describe the path of the jet stream, the timing of the jet stream. We describe synoptic troughs and ridges. The observed sequence of the storm tracks we prescribe, and we have every weather event that was observed at the right time and place. What is free in the model, so at least not explicitly constrained and touched by us, is SST, ocean heat content, sea ice, land surface, soil moisture, TQ profiles at all levels, cloud radiation, moist convection, and even, that's important, mesoscale dynamics as well, right? I mean, sort of Cape, SIN, and so forth. In principle, also MCSs could in principle be not entirely free perhaps, but have some own dynamics. And that's very interesting because some of the extreme precipitation events, they are not, if you really want to understand them in our experience, you have to understand mesoscale dynamics as well. And I think you can there's strong evidence that with this kind of configuration, you can actually do that. Let me just very briefly touch on one brief topic that I think is interesting and comes for free once you have these simulations, and that relates to model error diagnosis. And we have this beautiful expedition that some of you may have heard, Mosaic, where we took our icebreaker at RV, froze it for a bit more than a year into the Arctic and let it drift. And then we got beautiful observations from the full climate column, if you will, from the deep depths of the ocean all the way to the top of the atmosphere for every single day throughout a year in the new Arctic. And this Mosaic expedition came with this big promise of improving climate models. Okay, but I always was a bit stressed when they sold this as such, because I'm, as a modeler, they would ask me to then deliver better models. But the problem is, if you use high quality observations for a short period of time, it is impossible to get the right weather, to make things very comparable. So the differences are always, it's difficult to say, is it different weather or is it really different physics? But with this spectral nudging technique, we basically get a beautiful representation of the evolution of the weather situation, and then can focus on the interesting issues that remain. And this is from a paper by Felix Pitan. Similar plot is available for kilometer-scale systems in Armal's paper. And it shows you the observations from Mosaic here in black, and then it shows you our coupled system here in blue and yellow. And then you see that what's characteristic for that period was a strong mid-latitude warming event that happened to occur in April 2020, and you see how this is well captured, right? I mean, these warming and cool periods, different regimes in the Arctic, all nicely captured, so that you can really start to look into the physics of the model and how well they compare to the coupled system. And here you see, for example, an annual cycle strongly missing in the model, which clearly goes back to a simplistic treating of snow on ice and so forth. So if you're interested in more details, some of them are described in those papers. But I think that's something in terms of evaluating models more thoroughly, also with short, high-quality field campaigns, we haven't fully exploited yet. And I think it's also a nice and interesting way to evaluate, for example, EERIE models, against observations. If you're interested in terms of the data, they're available through the Destination Earth platform. They're a bit constrained. I think it's easy to get them as a European, more difficult if not. But yeah, that's the place to go if you are interested in exploring and working with the data. So a few key points at the end. My personal view is that these storylines provide a very promising additional way of looking into the future and doing attribution and so forth. It's not replacing anything, but it adds to the tool park that we have. Yeah, and it's it makes it very tangible, I should say. I think what we are able to do with that approach is to produce really great analogs in space and time. So this replaying works. And this in space and time is very important. I mean, if you want to really fully understand a heat wave or flooding event, you also need to understand the history of soil moisture and so forth of the weeks before. And finding good analogs in space and time from large ensembles is still almost impossible. Okay, and this is a powerful way of doing this. Again, I think very, very powerful. And that's also my experience when I show people plots from the general public. They say, that's what climate change means. And so very powerful as well. It allows us to separate the thermodynamic from the large-scale dynamic part. And certainly in the exotropics, a lot of uncertainty in terms of local climate change and extreme changes lie with large-scale dynamics. So you're separating the two, which is, I think, very nice, and something like an idea that Ted Shepard has been promoting also for a few years, sort of pointing that out as a very powerful thing and a reason to look into these storylines. There are other interesting applications of this approach. It facilitates coupled climate model evaluation, so you can, I think, exploit high quality data from campaigns much more easily and much more powerful. I mean, in a sense, this is like data assimilation, right? It's a sort of a simple form of data assimilation where you use nudging and a coupled system. But what you don't, I mean, usually people then say nudging are very bad and unbalanced and stuff. But I think one needs to point out that we are not nudging unbalanced, winds or something like that, but we are running something that has been already, that has sort of certain balanced geostrophic thermal wind and so forth. It has it already from the reanalysis, and I think therefore that makes it much more powerful than having used observations alone. It's also very nice to understand physics of climate change. I didn't really have the time, but I mean. But there's a paper by Marie-Lou on heat wave in the North Pacific, and you can really see how sort of the dynamics and the amplification and the scale of this changes in a warming world because the processes are changing, right? So looking at unfolding at the process level of extreme events, coupled extreme events, or in the uncoupled as well, and looking at them is a very powerful thing to do. And then last but not least, there are some exciting ongoing developments in Destination Earth. That is operationalization of this, including real-time capabilities. So we hope that this year we will be able to provide this first with a 7-day delay, but then the ultimate goal is to basically produce that information for the day for the 8 o'clock news in the evening. Okay, that's the ultimate ambition here, and perhaps even look sort of at the next 2 days, sort of a short weather forecast, counterfactual weather forecast for the next few days. Again, kilometer scale global configurations is very nice because you get lots of local granularity and detail, which is quite important when you want to look and consider extreme events. We are running this in Destiny at the moment with end-to-end with some impact models at the same time, hydrology models and so forth, but we would like to add more there, that you sort of get storylines, not just only of atmospheric and ocean parameters, but really of sort of impacts, like what is the level of water in rivers, what is the state of cities, the state of forests and so forth. And then there are sort of directions and exploring, by making this perhaps a bit faster, by using these AI-based emulators. But yeah, that's work in progress.